Hello everybody, my name is QV-Pham and I am a PhD student at the University of Tokyo. I am going to give a presentation on my paper, Correction of Displacement Response Estimates obtained from flow acceleration data using single degree of freedom analysis for building damage assessments. My presentation has six main parts: introduction, proposed approach for estimating low-frequency displacement components, case study for verification, methodology, results, and conclusion. To begin with the introduction, post-earthquake assessment of building damage is essential. Kusugi et al. Developed a method to estimate an equivalent single degree of freedom capacity curve of the building from recorded flow acceleration data. The displacement and acceleration capacity curve then can be used to evaluate the damage state of the building and to predict the extent of damage caused by aftershocks. The method has been applied and verified with many works and experimental structures, showing high reliability and applicability. This slide shows a flowchart of Kusugi et al.'s method. First, the flow accelerations are converted into displacement by using double integration. Then, discrete wave transform method is applied to decompose both acceleration and displacement by frequency bands, called ranges. Third, ranges corresponding to the predominant mode of response are selected and combined based on an algorithm proposed by USR, which considers various properties of each range, such as peak displacement, peak acceleration, bedfield slope, among others. Then, multi-degree of freedom displacement and acceleration response are condensed to an equivalent single degree of freedom system response. Finally, a capacity curve is generated from the backbone curve of the equivalent single degree of freedom static response. However, one problem of Kusugi et al. Method is that the displacement response obtained from acceleration response often contains no frequency noise induced by double integrating process. Therefore, no frequency displacement ranges are not selected because they are affected greatly by the noise. When the nonlinear response is significant, there may be large errors in maximum displacement. This graph shows the maximum displacement errors. The blue curve is the capacity curve obtained from acceleration, and the black curve is the reference obtained from recorded displacement response. This error could lead to an underestimation of damage state of the building. This study proposed an approach to correct the maximum displacement error of the capacity curve obtained from flow acceleration response by estimating the low-frequency displacement component from a single degree of freedom analysis of the building. First, the damping ratio was estimated from ambient vibration using half-power bandwidth method. The capacity curve was derived from recorded flow acceleration data using Kusugi et al. Method, then was fitted into a three-linear capacity curve. The unloading stiffness degrading parameter of Takeda hysteretic model were also estimated from the equivalent single degree of freedom hysteretic response. Then the equivalent single degree of freedom analysis of the building were performed, in which the mass of single degree of freedom system was the effective mass of the maximum displacement response, and the input ground motion was the recorded acceleration of the ground floor. Its next step, the displacement response of the analysis was decomposed by discrete wavelet transform to extract the no-frequency displacement component that corresponding to the frequency range of unselected no-frequency range. Finally, the no-frequency displacement component contributed to the maximum displacement of the building were taken and added to the maximum representative displacement of the capacity curve obtained from acceleration response. The proposed method was verified by using an experimental data from an ED fast tracking table set of a three-story reinforced concrete building. Figure 2 shows a photo of the specimen on the tracking table. Accelerometers were installed on all floors while laser transducers were installed between each floor to measure the inter-story drift, as shown in Figure 3. The displacement recorded by transducers were used to verify displacement obtained from the proposed method. The building was tested with 5 different scales of an artificial input ground motion as shown in Table 1: 20%, 100%, 150% first one, 150% second one, and 160%. Move on to methodology. By applying Kusugi et al. Method, equivalent single degree of freedom hysteretic response and the second skeleton capacity curve of the building were obtained from recorded floor acceleration response. The skeleton curve were derived based on the hysteretic response of all occurrence events mapped in sequence. Afterwards, linear capacity curve were fitted from the skeleton capacity curve based on a theory of equal dissipated energy and the ratio between the equivalent loss on the linear capacity curve and the original loss on the skeleton curve. Figure 4 shows the linear capacity curve estimated after 160% event, one capacity curve in positive direction and one capacity curve in negative direction. An average linear capacity curve was then calculated from capacity curves in positive and negative directions. If there no damage occurred before the analyzed event, the average linear capacity curve can be directly used for the single degree of freedom analysis. However, if the yielding had already occurred during a previous event, single degree of freedom analysis used a bilinear capacity curve that were created by combining the initial stiffness of the analyzed event and the derived average linear capacity curve as shown in figure 5. This is because possible degradation of the initial stiffness could have occurred. This study used Takeda hysteretic model to simulate the equivalent single degree of freedom response of the reinforced concrete building. In this study, unloading stiffness degrading parameter beta were calculated from the unloading stiffness of the outermost loop of the building hysteretic response. The unloading stiffness was the slope of linear fitting of response from the peak displacement to its intersection with the horizontal axis. And then beta were calculated by using equation 1. The estimated value of beta for 150% first run, 150% second run, and 160% events were 0.82, 0.6, and 0.615 respectively. This slide shows the full set of capacity curve correction of 160% event using single degree of freedom analysis displacement. Low frequency displacement components were extracted from single degree of freedom analysis displacement response by using deep regression form. Then the low frequency displacement component contributed to the maximum displacement were taken based on the maximum displacement time determined from acceleration based displacement. Finally, errors of maximum displacement of the capacity curve obtained from floor acceleration were corrected by adding the estimated low frequency component of maximum displacement. Now let's move on to result section. Table 4 shows the summary of proposed method result compared to the reference obtained from building displacement response recorded by chance user. In this table, D is a low frequency component of single degree of freedom displacement response at peak displacement time. AD is a maximum representative displacement of the building obtained from acceleration response by using Kuzuki-Asson method. As can be seen, the errors of maximum displacement obtained from acceleration response of 160% event were large, with over 20 mm or nearly 10% of the reference maximum displacement. The errors of acceleration based on maximum representative displacement of 150% event first run and second run events were less than 2 mm. For the 150% event first run and 150% event second run, the errors of combined maximum displacement were both under 5%. For 160% event, the combined maximum representative displacement were very comparable to the reference. The errors were less than 2% of reference maximum displacement. Based on the results, it could found that the estimated result of beta for defining the unloading stiffness of Takeda hysteretic model for different events were different. The values were greater than 0.4, which is the recommended value. For 160% events, the error was significantly reduced from almost 10% to below 2%. For 150% first and second events, contribution of estimated low frequency displacement component increased the errors. However, the errors were not large and the results were conservative. The single degree of freedom analysis result reduced the maximum displacement error of the event with large nonlinear response. Thank you for your attention.